Quick revision video on how to explain equilibrium shifts in terms of the equilibrium constants Kc and Kp. So we'll start by looking at temperature, and we need to know that equilibrium constants are changed by changes in temperature. So when you change temperature, the equilibrium position has to shift to give the new value of the equilibrium constant. So the rule is an increase in temperature will decrease the equilibrium constant for an exothermic reaction. Obviously it's going to do the opposite for an endothermic reaction. It's going to increase the equilibrium constant. So we need to remember those two facts. So we'll put that into practice now by looking at a couple of examples, obviously an exothermic one and an endothermic one. So starting with exothermic, so delta H is negative for the forward reaction. Just remember that rule, that the equilibrium constant, if we increase the temperature, is going to decrease. We also know from Le Chatelier's principle that we study in first year that an increase in temperature is going to favour the endothermic reaction. So we know that the equilibrium is going to shift backwards from our Le Chatelier's principle knowledge, but that's not enough if we have to explain it in terms of the equilibrium constant. So using the AB equilibrium, the Kp and Kc expressions would look like these here. So partial pressure of B over partial pressure of A, or equilibrium concentration of B over equilibrium concentration of A. So let's suppose at 300 Kelvin the equilibrium constant was 100, 500, it's lower. Remember, it drops when you increase the temperature. So how do you explain it? The ratio of partial pressures or the equilibrium concentrations need to change to give the new lower equilibrium constant. So how's it going to do that? Well, the denominator term needs to increase. So this term needs to increase to bring the equilibrium constant down to the new value. And so therefore, how does it do that? It moves to the left. So it's obviously going to be the opposite way around for an endothermic reaction, but we'll go through this one as well. So we already know that from Le Chatelier's principle. Our Kp and Kc expressions are the same as before, and all I've done for the values is just flip them round. Remember, we've got to get a high equilibrium constant now because we're increasing the temperature of an endothermic reaction. So how would you say it? The ratio of partial pressures or the equilibrium concentrations need to change to give the new higher constant. So now the numerator term needs to increase to make these Kp's and Kc's bigger, and so the equilibrium does that by shifting to the right. So moving on to all the other factors, we need to know that equilibrium constants are not changed by changes in concentration, pressure, or the presence of a catalyst. So now the equilibrium position shifts to maintain the value of the equilibrium constant, whereas for temperature it was shifting to give the new value. So we'll look at concentration first. So I'm going to use this equilibrium here. We already know from Le Chatelier's principle an increase in concentration of a reactant is going to cause the equilibrium to shift in the forwards direction. So in other words, to bring that concentration back down. So there's the Kc expression for this. Constant temperature, I'm saying Kc is 16 moles per decimeters cubed. So let's suppose at the same temperature, concentration of N2O4 is increased. How do we explain the shift in terms of the equilibrium constant? Well, the denominator is now going to be higher than it was before because we've increased the concentration of that. So this ratio of products to reactants is going to give you a lower value for Kc. It's going to be less than 16. So to get Kc back to its original value, the NO2 needs to increase and the N2O4 needs to decrease. And so the equilibrium does that by shifting to the right. So again, you've got your year 12 Le Chatelier's principle knowledge here to help you get started, and then that's how you explain it in terms of the equilibrium constant. So if we look at pressure now, it's the same equilibrium as before. So we know from Le Chatelier's principle an increase in pressure is going to favour the side with the fewest moles. So we know this one's going to go backwards. So how we're going to explain that one? So let's suppose at the same temperature the pressure of the system is doubled. There's your Kp expression for this equilibrium. Doubling the pressure is going to double all of your partial pressures because they're all in the same reaction vessel. So all of the partial pressures are going to change by the same factor, but the numerator term in this case is going to be affected more because the change in partial pressure is squared. So the ratio of partial pressures is going to increase the value of Kp. So how does it get it back down to its original value? The partial pressure of that needs to decrease and the partial pressure of that needs to increase. So therefore it's going to move backwards to the left to restore the Kp value. And finally, the effect of catalysts on equilibrium constant. So there's the Haber process with its ion catalyst. Presence of a catalyst does not alter the value of equilibrium constant or position of equilibrium. That's because the catalyst increases the rate of the forward and reverse reactions by the same factor. So the equilibrium is just reached quicker. Its position doesn't change.